Hello and welcome to another lecture for stats. In this lecture we will be talking about two sample tests. So up to this point we have looked at various different ways to do tests, inferential statistical tests with one sample. So we're looking at comparing a hypothesized mean or a sample mean to a hypothesized mean. So we've got the example of average age. So we've got an average age of Detroit Mercy students, and we are comparing that to the national average. So we're comparing a actual sample to a hypothesized mean. There's various different ways to do that. We covered those last week. In this week, we're now going to start, well, what happens if you've got two samples? And later on, we'll get to what if you've got more than two samples, and we'll look at ANOVA. But right now, we're going to look at what if you've got two samples. So instead of looking at average age of Detroit Mercy students, comparing it to the national average, let's say we were looking at the average age of Detroit Mercy students and comparing it to the average age of Wayne State students, something like that. So in these cases, we are making a comparison between two samples. We're trying to see if one's greater than the other, if one is different than the other, if one is less than the other, that type of thing. So it's when we've got two samples. When we are doing two sample tests, there are two types of two sample tests we can do. And you can actually do these for any statistic, any descriptive statistic that we talked about earlier in the semester. For the purposes of here, we're just going to look at the mean, but you could also do it with correlations, you could do it with proportions, all of those other things like we did with the one sample. But for the purposes of this lecture, we're just going to look at means, sample means. In the two types of tests you can do, and it's important to know when to do which test, is the two types are independent samples tests and paired samples tests. So independent test and paired test. We'll get to it later of how you make the decision between the two. But making a decision between an independent test and a paired test is an important step, just like making the decision between a one sample test and a two sample test. But that's an easy decision to make because if it's got two samples, it's a two sample test. If it's got one, it's a one sample test. Just like the distinction between a z-test and a t-test. Whereas you do a z-test when the population variance is known, you do a t-test when the population variance is not known. That type of thing. Well, those are important decisions you have to make when determining what test you're going to do, also whether you're going to do an independent or a paired samples test. You see on this slide that there is z-tests and t-tests for independent samples, but there is not for paired. That's because a paired samples t-test, paired samples test is always going to be a t-test, whereas in independent samples you can do both a z and a t. There is no way to know the population variance in a paired samples test, so you always have to do a t-test. But we will come back to that. So why do we do two sample tests? And I already talked about this. Instead of being interested in one specific value of a parameter, we're interested in the relation or difference between the value of two populations. So we draw two samples, one from each population, and we look at the comparison between the two. Let's start with independent samples tests. So independent samples tests are when you have two independent samples. When I'm explaining paired samples, I'll come back and explain exactly what I mean by that. But with independent samples, you've got two independent samples tests, you've got two independent samples. And what we are going to do is we are going to do z-tests or t-tests for differences between the means. So we've got two independent samples. We are looking at the sampling distribution of the difference between the means. So last week, you recall, we were looking at the sampling distribution of one mean. Now we're looking at the sampling distribution of the difference between two means. So in this case, we are looking at the difference between two means rather than an individual mean. Now when we're doing the independent samples, it's a little bit more of we're looking still at both means. When we get to the paired samples, we'll talk about that, and that we're really just looking at the difference. You can do an independent sample z-test if you have a known variance, population variance. However, if you must estimate the variance and the standard error of the difference between the means, we do an independent samples t-test. So the two ways that we do the distinction between a z-test and a t-test is the exact same thing for two samples. That is, we need to know the population variance for both samples to do a z-test. If we don't know the population variance for either sample, we have to estimate them. We do an independent samples t-test. Our hypotheses for two sample tests are written like this, and this is for two independent samples. We write them like this, but again, there's only three different possible pairs of signs you can have: less equal to and not equal to, less than or equal to and greater than or equal to and less than. And that's the same as before. But now we've got a little bit different of how we write the rest of the hypotheses. So we'll look at the non-directional at the top. You see that you've got mean 1 minus mean 2. So population mean 1, population mean 2 is equal to, and essentially this is going to be 0. Now, if for some reason you are given a hypothesized difference to compare it to. So let's say you think that mean 1 is at least 10 different than mean 2. Then you would have you would have, in that case, the hypothesized difference here would be 10. But for everything you're going to do in this class, and for all intents and purposes, 99.9% of times where this is done as a test, the hypothesized difference is going to be 0. So you don't put so the d of 0 is basically what that's saying, a difference of 0. You can, if instead of putting d of 0, you just put 0, that's fine. If you put d of 0, that's fine as well. The point is it could be something other than 0, but you'd have to have a hypothesis that basically states that you're comparing it to a difference other than 0. At no point in this class will we do that, though. It will 100% of the time be 0. And then the alternate hypothesis is mean 1 minus mean 2 is not equal to a difference of 0. And the same for the directionals. It just comes down to difference of 0, less than, greater than, something to that effect. Okay, so what is going on here? And this goes back to one sample. Remember, with one sample, we needed to have a sampling distribution of the means. We did that by basically, it's a hypothetical thing, but it's all possible sample means that could be taken of a fixed size from the population. Well, a sampling distribution of the difference between the means is all possible differences between a possible sample, all sample means for sample 1 and all sample means for sample 2. So in a sense, it's the same thing, but instead of it being a distribution of means, it's a distribution of the difference between means. So just like with one sample, if the distribution is normal, in the samples, the sampling distribution of the difference between the means will be normal. If not, we just rely on the central limit theorem. So for the purposes of in here, just assume that they're always normal, or that the central limit theorem is kicked in enough to make it normal. So when we're looking at this, you've got your mean of your sampling distribution here. That is the mean of the difference between the means. And then this is going to be the variance of the difference of the means and the standard deviation of the difference between the means, or the standard error of the difference between the means. For the purposes of what we're doing in this class, this is more of just the theoretical side, so you understand that when we're doing two samples, we're doing it in a way that's very similar to one sample, except instead of looking at one sample mean, we're looking at a difference between the means. Just like with the sampling distribution of one mean, you now have a sampling distribution of the differences between the means. So it's all possible difference between the means that you could get from drawing a fixed samples out of the two populations. Okay, so our basic formula, our starter formula for the z-test for the difference between the means is what you see here. However, we're going to break this down and make it easier because obviously you're not going to know straight up the standard error of the difference between the means. We're going to take it, you'll know a variance or a standard deviation of mean 1 and a variance or standard deviation of mean 2, as well as a mean of 1 and a mean of 2, but for the purposes of in here, we are going to just look at, we're going to extrapolate it and take it from what you see here, which you can't know, to what you know. The same way we did with the one sample test. Sorry if I got a bit confusing there. I do want to point out something, and I'll point this out a few times. While this is in the formula, what you see here, what is here, is always going to be 0 for the purposes of figuring out in this class. Going back to what I was saying with the hypothesis, if the hypotheses had a hypothesized difference that you were comparing it to, rather than just trying to see if there's a difference, or to see if one's greater than the other, then this wouldn't, that I have circled, would not be 0. But for everything we're going to do in here, since the hypothesized difference is 0, that is going to be 0. You could just take that off from the formula entirely. Again, we're extrapolating here. The mean of the difference equals mean 1 minus mean 2, or the mean of means 1, mean of means 2. But if you remember, the mean of means is just equal to the mean of the population. Therefore, we've got that there. It's always going to be 0 in here, but that's besides the point. We'll come back to that. The variance of the differences is equal to the variance of the means of 1 plus the variance of the means of sample 2 minus 2 times the standard deviation of 1 and 2. For the purposes of in here, if the samples are independent, that's always going to be 0, so that can be just taken out. This goes back to the additive principle, if you remember, when we were doing probability, and you had to take out the overlap. Well, if their samples are independent, there is no overlap. So the first step we have here is getting to this point. However, we need to take it one step farther because, again, we know the formula for this. So we've got, again, the variance of the difference between the means of the sampling distribution of the difference between the means is equal to the sampling distribution of the variance of sample 1 plus the sampling distribution, the variance of the sampling distribution of sample 2, but that equals the variance, so that the variance of the sampling distribution of a sample is equal to the variance of the sample divided, or the variance of the population divided by n. So we can substitute this in for this. What does that mean? We can substitute in the variance of sample 1 divided by the n of sample 1 plus the variance of sample 2 divided by the n of sample 2 for the, in place of the variance of the differences between the means. This is just looking at it in another way. Again, standard error, the standard deviation is just going to be the square root of the variance, hence why you've got this equal to this. We already talked about this up here, so we don't have to worry about that. Let's actually get to the final formula now. So our final Z formula is going to be the mean of sample 1 minus the mean of sample 2 minus the difference in means between the two populations. However, I already said this is always going to be 0 for in here, so we can just take that out. We're not even worried about that. divided by, and it's going to be the standard error of the differences between the means, which is the square root of the variance of sample 1 divided by n of sample 1 plus the variance of sample 2 divided by n of sample 2. And just like I said before, population variances must be known to do the z-test. But you do not have, what I X'd out there, you do not have to do that you don't even have to write it from this point on. I've got it here because it's part of the formula for it, but as I said before, for the purposes of in here, that's always going to be equal to 0. So it's not even something to be concerned with. Now, I didn't have an example of that. I'll do an example of that in the review for the exam, but let's actually move on to what if you don't know the population variances. And the majority of the time, this is going to be the case. As just like with one sample, with two sample, we don't typically know the variances of the populations. So we have to instead estimate the variance of the populations. We do this in a very similar way to what we did with one sample test, except now we're doing the estimated variance of the differences between the means. And actually, that's the estimated standard deviation. If you have the estimated variance, you just take the square root of that to get that. So we do this we do a t-test instead, just like we did with one sample. Just like with one sample, you need to use the t-chart. To use the t-chart, though, you need degrees of freedom. With an independent samples test, the degrees of freedom is equal to n1 plus n2 minus 2. That is because there are two possible points of variability, because there is a sample 1 and a sample 2, so it's sample 1 n plus sample 2 n minus 2. So if you have a sample of 10 and a sample of 10, it's going to be 10 plus 10, 20 minus 2, so 18. Your degrees of freedom is 18. Our formula for estimated standard error, if I can get this to right, is what you see here. So there is quite a bit to it. It's going to be the square root of the sum of squares for sample 1 plus the sum of squares for sample 2 divided by n1 minus 1 plus n2 minus 1. You could also here do n1 plus n2 minus 2. In a sense, this is the degrees of freedom here. And then you have to multiply that by 1 divided by n1 plus 1 divided by n2 and take the square root of all of that to get your estimated standard error of the differences between the means. That is quite a bit. And you notice there that there isn't, the steps aren't one farther, which is if you're given the variance or the standard deviation of the sample. So for this test, you're basically going to be given it from scratch. You might be given the sum of squares, but you might be just given it from scratch and you have to calculate sum of squares like we did, and I believe it was about week 3 we calculated sum of squares. It was week 2 or week 3, I think it was week 3 we calculated sum of squares. So you have to go back to being able to calculate that. So like I said at the beginning of the semester, stats isn't cumulative for exams other than the fact that we build on previous knowledge. This is one of those cases where you have to take the previous knowledge and continue to use it. So our final t formula, this looks pretty big, it looks pretty complicated, but again, just like with the z, that is always going to be 0. So you can just take that out, and really you're going to calculate out a mean for sample 1 and a mean for sample 2. The hardest part is going to be calculating out the sum of squares for sample 1 and sum of squares for sample 2. And this is where you've got to go back and use those formulas from earlier in the semester. I will go over that again here on the next couple slides, looking at it really just briefly, but then I will do it again in the review. So let's look at an example of that. An example of that, because this is in the homework. You notice I didn't give an example of the z-test. I'll go back and I'll use an example in the review, but I'm not as concerned about the z-test because that's not as practical, that is not as common. So it don't expect to have to do the z-test on the homework or the exam. But that being said, I'll still show an example of it in the review. But this, I would expect to know it's definitely in the homework and it could be on the exam for independent samples t-test. So we have a researcher wants to determine if people who watch PBS and those who don't watch PBS differ in terms of cognitive complexity. Randomly samples 8 people who watch and 6 who don't and conduct an appropriate statistical test. So some things we can determine here: N1 equals 8, N2 equals 6. I'll come back to this later, but here's actually a kind of important thing that you can use to determine whether you're going to do an independent samples test or a paired samples test. A paired samples test, the ends of sample 1 and sample 2 will always be equal. In independent samples tests, they may be equal, they may not be equal. So just because the ends are equal doesn't mean you do a paired samples. The ends could be equal and you do an independent, but if the ends are not equal, you always know it's a independent samples test. So if N1, if I can get this right, N1 is not equal to N2, independent. So in this case, N1 is 8, N2 is 6. They're not equal. You know right away it's an independent samples test. You are not given population variance. You're not given population standard deviation. So now you know that it is a t-test. So it's going to be an independent samples t-test. So our hypotheses are going to go from that. First, you've got mean of sample 1 minus, or mean of population 1 minus mean of population 2 is equal to 0. That's your null. Your alternative is that they're not equal. We are doing a t-tests because the population variances are not known, but I'm going to actually write on this because this is a independent samples t-test. Now, population variances is not known, you don't have to write, but I expect you to here write at least independent samples t-test. Independent samples is stating that it's an independent samples. There's 2 independent samples. T-test stating that you're doing a t-test, not a z-test. Sometimes you can write 2 independent samples t-test, or you could just write independent samples t-test. Either would be fine, but this is the minimum of what's required for step 2. So if you just write what's in text on step 2, you will get that wrong because you didn't write independent samples. Step 3, it's a two-tailed test or a non-directional test. You could say either. That is because the null and alternative hypothesis are equal and not equal. Step 4, our alpha is 0.05. Our N1 and our N2 both need to be listed because, again, step 4 is state your alpha, your N, and your degrees of freedom if applicable. So because we've got 2 N's, we have to state them both. Alpha 0.05, N1 of 8, N2 of 6. And our degrees of freedom, again, is N1 plus N2 minus 2, or 8 plus 6 minus 2, and that's 12. In step 5, we have that big long formula, even though this is going to be 0 here, so we don't even really need to worry about it. But we need to calculate out our sum of squares. We can't just do the formula or do this. We need to first calculate out our means and our sum of squares. And that's what we'll get to on the next slide. Looking at this, now let's look at it. And if you remember, the sum of squares formula is what you see here. So it's the sum of x squared minus the sum of x, and then that squared divided by n. So this would be n1 and n2. And to do that, I already did all the math here on the right, but you take in to get sum of x, 1, that's here, you just take and sum the x's. So that's 111. Then you take x1 squared, over here and sum that. And that's what you get here. The sum of x squared is 1645. And then, of course, n1 equals 8, n2 equals 6. So I kind of showed the steps of doing this, but the sum of x squared is the first thing here. That is equal to 1645. Then this 1540 is actually all of the after the minus done, and you can look down here on the right and see that. So first I took the sum of x, which was 111. Then the next step down I squared that, 12,321. And then I divided by n, which was 8, and got 1540.125. So the sum of squares x is equal to 1645 minus 1540.125, or 104.875. And sum of squares x2, same way. You do the sum of x squared 2, which was 451 over here. Then the sum of x, which is 51, square that, then divide that by 6, and you get 433.5, and you get a final of 17.5. The last thing that you need to do is calculate the means, which I didn't do here, but you get, to calculate out the means, you would do the mean of x1 would be equal to 111 divided by 8, which is something like, what is it, 13.875. And then the mean of x2 would be equal to 51 divided by 6, which is equal to 8.5. Now we have everything we need. We have our mean of x1, our mean of x2, our sum of squares of x1, and our sum of squares of x2. We've got n1 and n2. We just need to plug those into the formula. When we plug everything into the formula, and yep, I was right on the mean of x1 and x2. When we plug everything into the formula, we get a t with degrees of freedom of 12 equal to 3.116. Step 6 is find our critical value. For this, we will go to the t critical chart. We have a non-directional two-tailed. We have an alpha of 0.05 and a degrees of freedom of 12. From the t chart, you will get the t critical value of 2.179. Now we need to step 7. So step 6 is get the t critical. Step 7 is make the comparison. The absolute value of our t observed is greater than the absolute value of our t critical. Therefore, we reject HO. Step 8 is state it in terms of the problem. So we've got given an alpha of 0.05 and a t with degrees of freedom of 12 equals 3.12. Reject HO and conclude that those who watch PBS are significantly more cognitively complex than those who do not watch PBS. You notice I use the word significant here. This is a bit different than the writing I did last week where I said statistically significant, or there's a statistically significant difference, things like that. And this is just showing another way to write it. As long as you still include that word significant when you reject, and you do not put the word significant in when you fail to reject, it's still going to work. So this is just showing there's a significant difference by saying that those who watch PBS are significantly more complex than those who do not watch. Now you notice that the step 8 here, it's talking about one being greater than the other, even though the hypotheses were non-directional. That is because even though the hypotheses are non-directional, we can look and see that those who were in the watch PBS group are greater than the non-PBS group. Because of that, the PBS group was an average of 13.875, the non was average of 8.5. So we can determine that the PBS group was greater than. So we got a significant result on just a non-directional difference, but we can actually look at the the means in our samples and figure out which one is greater than the other and put that in our step 8. So that is the independent samples t-test. Kind of easy to do. The only complex thing is you have to figure out the sum of squares and the means, but that's stuff you should already know how to do from earlier in the semester, so it's not that much. This will be on the homework, and it'll probably be on the exam as well. It's one of the main tests that are out there in the sciences is 2 sample tests. Let's look at the other 2 sample tests now. So now we are going to look at the correlated samples or paired samples t-test. You're gonna always hear me call it paired samples, even if correlated samples is another term for it. I just tend to always call it paired samples. It's just the statisticians that taught me called it paired samples. Other statisticians call it correlated samples. So you'll see it both ways in these slides, just because a lot of the stuff I heard once I got to grad school and stuff called it correlated, even though my undergrad classes called it paired. So again, you see it both ways. It's just a matter of 2 different names for the same thing. So there's going to be 2 different types of paired samples. And when we look at when do we do or why do we do a paired samples test? First off, if you can do a paired samples test, you always do a paired samples test because a paired samples test has more power. So a paired samples test has more power over versus a independent samples test. So if you can do a paired samples test, you do a paired samples test. This is just like when I talked about before. If you can do a directional test, you do that over a non-directional, but you need a hypothesized reason to do it. Well, if you can do a paired samples test, you do it. That being said, there are specific requirements that must be met to do a paired samples test. And the main thing is that you must have a logical pairing mechanism. That came out really weird with the word pairing. Either way, you have a logical pairing mechanism. What do I mean by a logical pairing mechanism? That is one of 2 ways that can occur. The first is with a repeated measures design. A repeated measures design is when you're doing a within subjects design and doing a pre and a post test, or doing 2 tests on the same group. So you have the same individual, the same participants. If you're looking at it in terms of not even just humans, but like companies, the same company. If you're looking at it cities, the same city, but where you're doing the both conditions on the same city. So the previous one, when we did the independent samples, was looking at, well, when you're testing 2 different samples of people, and one sample watches PBS and one doesn't. Well, what if you had one sample of people that one watched PBS, that group, the entire group watched PBS and then took a test, and then they spent a week not watching PBS and took a test? Well, now you've got a repeated measures design. You've got this logical pairing mechanism in that both tests were done on the exact same participants. So this is where your individuals, companies, cities, whatever, are tested at 2 different points in time. So that's the first, repeated measures design. Repeated samples on the same participants. The other is matched pairs design. Matched pairs design is a little bit trickier, but this is where you matched pairs based on this pairing mechanism. So in repeated measures, the pairing mechanism is that the individual it's before and after. It's 2 different times. So the pairing mechanism is just it's the same individual. But a matched pairs design, the pairing mechanism has to be some justifiable third variable that pairs the individuals together. The individuals from each pair can be randomly assigned to one of 2 conditions. And in this case, you've got, let's say you're testing something and you want to see about 2 different individuals that have a logical third thing, like they're both extroverted. So you've got a sample and you've got 2 different samples and you pair people on their level of extroversion. So that would be a pairing mechanism. That's pretty difficult to do. That's rare to do. What is more likely is this at the bottom. That is that pairs are formed on a logical basis for matching. This is like if you did identical twins and you assigned one identical twin to one condition and the other identical twin to the other condition. Or if you had couples. So you assign the men to one condition and the women to another condition, but you've got a logical pairing mechanism. There's some mechanism that pairs them together that makes it so you can say this individual from sample 1 is tied to this individual from sample 2. We have them paired. It is paired in that case. So the individual from sample 1 is paired to the individual from sample 2. I hope I've explained that well enough, but this is how you decide whether you're doing a paired samples test or an independent samples test. A paired samples test, you've either got before and after testing, or you've got a logical pairing mechanism. Independent samples, there's no way to pair individuals or participants from sample 1 to sample 2. When we do a paired samples test, it actually gets much simpler. What you do in a paired samples test is the first thing you do is you find, so this is step 1. Step 1 is you find the difference between each pair. So let's say you're testing husbands and wives. You find the difference between the husbands and wives. Let's say we're looking at husbands and wives child care behavior. Actually, that's going to be our example later. Let's say you were looking at twins and one twin got assigned to take Tylenol and another twin got assigned to take a new painkiller drug. And then you have them do a task that would cause pain, like stick their hand in cold water, ice cold water, and see how long they can keep their hand in the water. And the logic there is that keeping your hand in the water longer means you feel less pain. So we want to see if the new drug is better than aspirin or Tylenol, whichever one you choose, at treating pain, at reducing pain. You assign one twin to the aspirin condition and one twin to the new painkiller. The first step would be to take the difference in each pair. So let's say you've got 10 pairs of twins that you had do this. The first thing you would do is take the difference between the twin in sample 2, the new painkiller, and subtract the score they got, the score that twin 1 got on that got aspirin. So what you get is you get 10 different scores. You no longer are interested in the individual scores because now for step 2 you conduct a one sample t-test on the different scores. So let me get to, we'll come back to that and I'll explain it a little bit more when we get to the actual example, what I mean by that, because you can't see it here. But let's say you've got sample 1, sample 2, you get a score of 5, 6, 5, 4, we'll just do 4 participants. Sample 2, you get 4, 4, 3, 2. First thing you do is you take a difference. So we're going to take, in this case, we're wanting to see if sample 2 is lower than sample 1. So we would take sample 2 away from sample 1. So it'd be sample 1 minus 2. We get 1, 2, 2, 2. Now that we've done that, so the first thing we did is that we just did step 1 and got the differences. So this was step 1. Now step 2 would be to conduct a one sample test on these differences. Once you've done the differences, the initial scores, the original scores, no longer matter. You can just get rid of those because the original scores no longer matter after you've obtained differences. Like I said, I'll have the example later and we'll look at that again. Hypotheses here are similar to the independent samples hypotheses, except now it's the mean difference. Not the difference of sample 1 minus the difference of sample 2, it's the mean difference because we're doing the test on the differences. And again, this is going to be 0, so you can just put 0 there. Just like with one sample t-test, where we had the sampling distribution of the means, we've got now a sampling distribution of the differences. So an independent sample test had a sampling distribution of the difference between mean 1 and mean 2. This is actually just a sampling distribution of the mean differences. We can never know the variance of the difference. It's not possible to know. That is why we always, so because we can't know it, cannot do a z-test. Can only do t-tests. So cannot do a z-test, can only do t-tests. Because we always use the variance estimate here. And again, extrapolating out, what our final formula ends up being is essentially this, because and we'll take it one step farther, but the estimated variance of the differences, we'll look at that in a minute, but it's just like, again, in the third week of class where you calculated the estimated variance, you do the same thing here. You calculate the estimated variance to get your estimated variance of the differences. You calculate the estimated variance on the differences. And so paired samples t-test, our degrees of freedom is back to n-1 because we no longer have two samples that we're looking at. We're just looking at one sample of differences, one set of differences. Let's look at an example here. So a researcher did a study to determine if there was a difference between husbands and wives in child-rearing behavior. This is why I said before I didn't want to do this as the example before, because I'm going to use it now. So the number of child-rearing behaviors per day is measured for 10 pairs of husbands and wives. The pairing mechanism here is the couples, so there's a logical reason to pair them. In this case, in the top one here, that's husband 1 and wife 1. You wouldn't pair husband 1 with wife 10. You'd pair husband 1 with wife 1 because they are married. So that you've got your logical pairing mechanism is the couples. Even if they're not married, they're couples. You get their child-rearing behaviors. So these are the child-rearing behaviors for husband 1, child-rearing behaviors for 2, and the first thing you do is you calculate a difference. So since we are doing, if you look at the researcher wanting to determine, we now need to determine which way we're going to do our difference, which set, husbands or wives, we're going to subtract from the other. But because we're just looking for a difference, this is non-directional, it doesn't matter which one you subtract from the other. You could subtract the wives from the husbands or the husbands from the wives. It's going to be the same thing because in the end you're going to take absolute values. That being said, if it's directional, let's say we wanted to see if wives had greater helping behavior than husbands, was our hypothesis. In that case, we would want to take the helping behaviors of husbands away from wives. Therefore, the wives is the first. The one we think is greater is going to be the first. The one we take the one we think is going to be less away from the one we think is going to be more as part of our calculating the difference. And then we can get the proper signs for the differences. But this is step 1 here. Step 1 is get the differences. You notice the one with the parenthesis there looks like a D. Completely coincidental, but Step one is to get the differences. So first thing we do is we calculate those differences, and we've got this set of differences, and we do our statistical test on those differences. We no longer care about what's over here once we've calculated those differences. We want to conduct an appropriate test using an alpha of 0.05. Well, first things we need to do is calculate the standard error of the estimate, the estimated standard deviation. So to calculate that, it's equal to the sum of squares divided by n minus 1. And this is actually the variance, not the standard deviation. So the estimated variance, we want to calculate the estimated variance. That is equal to sum of squares divided by n minus 1. Sum of squares, that same thing we calculated a few slides ago, is going to be equal to the sum of x squared, which here is differences now, since our x's are differences, 193. So it's going to be 193 minus negative 21. So this will be negative 21, 193. But we need to take negative 21 squared, and our n was 10, if you recall. Negative 21 squared is 441, but if we divide it by 10, we get 44.1. So our sum of squares is 148.9. Plug that into 148.9 divided by n minus 1 divided by 9. We get an estimated variance of 16.54. So now we have the information we need to plug it into the formula, except we need a mean of the differences, which is going to be equal to negative 21 divided by 10, so negative 2.1. So our hypotheses here, again, our null is that the difference is equal to 0. Our alternative hypothesis is that there is a difference, so the difference is not 0. This is a paired t-test for correlated samples, or a paired samples t-test. It's non-directional. Our alpha is 0.05. Our n is 10 because our n that we're concerned with is the pairs. With a paired samples test, we're no longer concerned with at any point the individual samples. We're concerned with the sample of pairs. So our n is 10 because we had 10 pairs. Our degrees of freedom is n minus 1. Number of pairs minus 1, so 9. For our formula here, and I didn't say this before, but just like with the independent samples, the hypothesized mean difference here for this class is always going to be 0, so you can just take that off. You don't even have to worry about it. Our mean difference was negative 2.1. Our estimated variance was 16.54. We divide that by 10 and take the square root of it. We get a t with degrees of freedom of 9 equals negative 1.663, or negative 1.633. Step 6, so we've got our observed there. Step 6 is to find our critical, so we'll go to the t-chart. We've got two-tailed because it's non-directional. We've got an alpha of 0.05. We've got a degrees of freedom of 9. So go to your t-chart, looking at a degrees of freedom of 9 with an alpha of 0.05 that's non-directional, and you get a critical of 2.226 or 2.262. I cannot talk today. Step 7 is make a comparison. So here we've got our absolute value. It's a non-directional test, so you can use absolute values. Absolute value of negative 1.633. However, it is less than our critical value, so our t observed and our t critical. Our t observed is less than our t critical, therefore we are going to fail to reject HO. And from there, step 8 is state it in terms of the problem. This should actually be 9. So given an alpha of 0.05 and a t with degrees of freedom of 9 equals negative 1.63, fail to reject HO and conclude that there's insufficient evidence to indicate that husbands and wives differ in number of child-rearing behaviors exhibited. Well, there was a difference. The difference was not significant, so therefore we cannot determine that there is a significant difference. We do not use the word significant because we failed to reject HO, so we say there's insufficient evidence to indicate that there's a difference. So that is the paired samples test. So we got the independent samples test, the paired samples test. Again, you're going to have to determine in the homework and the exam whether you're going to do a paired or independent. If you have a logical pairing mechanism, you do a paired. If not, you do independent. That's actually a pretty good question for me to ask on part A. I might put that on part A. What's the difference between a paired and an independent samples test? Or when would you do a paired samples test over an independent samples test? Very simple answer, when there's a logical pairing mechanism. All right, there's one final thing I just wanted to cover real quick, just because this was a relatively short lecture week, so there wasn't as much to talk about. I did want to just add in one minor thing, and that is effect size. So when in statistics, why is effect size important? Effect size is important. You remember when we talked about power, because the larger the effect size, the greater the power. Effect size is important though because effect size is basically saying how much of an effect there is. And significance testing is kind of strange in that as your sample size increases, you become much more likely to find significant differences. When you've got a sample size of 1 million, so to say, you can have very minuscule differences that aren't even noticeable in any shape or form other than through extensive testing. You can find those significant differences though when you've got sample sizes that large. What is important, just as important as finding a significant differences though, is effect size. And effect size is basically measuring the amount of variance in the dependent variable that's accounted for by the independent variable. So if I had two drugs and I was testing the amount of time you could, two pain drugs, I was measuring the amount of time you could keep your hand in water. And I had 1 million participants and 1 million people in sample 1 and 1 million people in sample 2, and sample 2 could keep their hand in the water for 0.001 seconds longer than sample 1. That would come out as significant because the sample size is so large. However, that's not really a difference. Even if I had a sample size of 1 million, if people in sample 2 kept their hand in 10 seconds longer than sample 1, now that's a larger effect. So then we deem that even though they're both significant, the second example has a greater effect because you actually have a noticeable effect. I talk about this as analogous to the coefficient of determination and correlation. We haven't talked about correlation yet, but what is R squared in correlation? So R in correlation is looking at the relationship between two variables. R squared in correlation, which we'll talk about in the second to last week in just a couple weeks, is R squared is looking at how much of the relationship or how much of the difference in one variable is explained by the other. Well, effect size does the same in samples like this, in that we're looking at how much of the variance, how much of the variability in the dependent variable and our outcome variable is accounted for by the independent variable. So this is a strength or a magnitude of the association between these, and this is referred to as an effect size. There's 3 ways that you can calculate effect size. Actually, there's 100 ways you can calculate effect size or more. There's 3 main ways. Each is more stringent. Each is more restrictive. So each is a better way of calculating it. However, the basic way that people calculate effect size is with eta squared. Epsilon squared is another way that's done, and omega squared is another way. Each of them gets slightly more restrictive, as I said. Each of them, there's arguments for being slightly more restrictive, so slightly more conservative. So the modern one that's used the most is the omega squared. You see each of these is done with t-tests because you need a t-value, you need a t-observed statistic. So these t-values are the t-observed values. These aren't the t-critical values, these are the observed values you obtain from doing the test. So if you do the test, you get a t-value, then you just have to throw in those t values into this formula. The eta squared is just your t value squared divided by your t value squared plus your degrees of freedom. And this is where the degrees of freedom you see here in eta and epsilon, and then n1 plus n2 and omega is how sample size is controlled for. So as I said before, a sample size of 1,000,000, you've got to have a bigger effect to have a, or you have to have, you can find a significance with a smaller effect. This, in these formulas, degrees of freedom or n1 and n2 controls for that. Let's actually look at each of these calculated out. So let's say we've got a n1 of 8 and n2 of 6. Recall this is from our independent samples test. A t observed of 3.116 and a degrees of freedom of 12. This is everything that came from our independent example. To calculate eta squared, you just do that t squared, so 3.116 squared divided by t squared plus degrees of freedom of 12, and you get a 0.4472. Multiply that by 100 and you get 44.72%. What is this saying? That 44.72% of, and what was the thing we were looking at? Variability. We looked at, it was variability in, it was PBS, watching PBS. It was cognitive complexity. That's what it was. So 44.72% of cognitive complexity was accounted for, was explained by, and 44.72% of variability in cognitive complexity. So variability, so 44.72% of variability in cognitive complexity was explained I can spell today, was explained by watching PBS. So 44.72% of variability in cognitive complexity was explained by watching PBS or not. I'm not going to do that for each of these, but that's just saying what this percent is. So eta squared, it's going to have the biggest amount, the greatest amount of variability. So it is in a sense the least. It is the one that eta squared is the one that was initially used. Then we get epsilon squared. Epsilon squared is basically saying 40.12% of the variability, and then omega squared is saying 38.35% of the variability in cognitive complexity was explained by PBS watching or not. And this is the most conservative one because it's basically saying the least amount of the variability was explained. All right, very simple stuff. When it comes to effect size, it might seem like there's more there, but it's just very simple. It's just explaining how much of an effect there is, how much of the variability is explained by the dependent variable is explained by the independent variable. That's all I have for this lecture. Later this week, I will have the study guide posted. Thanks. Come on back.